Before we proceed, I just want to check. Do you see the PDF file on your screen on distribution networks?
Yes.
Okay, thank you very much for that. Mm, Okay. Okay, let me just open that screen. Okay. In today's lecture, which I actually meant to do on in Monday's lecture, I do apologize for that. It seems like the protesters are able to actually get into MS Teams also. Hopefully, we've resolved that issue, and hopefully there won't be any disturbances in this lecture. And, I want to look at the next section on potable water distribution networks. Potable meaning drinking water. That simply that's what it means. And then a water distribution network. We look at the analysis and design of it. What we're leading up to is the Hardy-Cross method, which is a method for designing looped networks. That you've done in last week. I had given you a tutorial to do, and I've given you an example for a single branch pipeline to design a single branch network. So we now want to do looped networks, and in order to do that, we'll first cover some little bit of theory about layouts and things like that, and then in next week's lecture we'll do the Hardy-Cross method. In this particular lecture, we'll look at the methods of distribution, systems of supply, and then we'll spend some time on the layouts of distribution systems, the typical layouts. As a designer, you will look into, you will make a decision into what type of distribution system you want, and then guidelines for the design of a distribution system, and then the actual design of a distribution system. That's what we're going to get into. Uh, just a brief introduction. Generally, in the South African context, we don't use too much of desalinated water. We also there are a few places where we have borehole water, but generally our water is derived from rivers and dams. So the water flows from rivers into dams. It's stored in dams, and then from the dam it is then treated and then distributed from there. Right. So we're looking at when talk of raw water. Raw water is the water that's in your rivers and in your dams, so it's untreated water. Right? So it may or may not necessarily be fit for human consumption. It might be quite turbid, meaning it might have sand particles in it or dust particles or other contaminants in it. So we generally refer to that as raw water. Right, so raw water from dams and rivers, that's mostly in the South African context. It then has to be treated or made safe for human consumption. So it's treated in a water purification plant or a water treatment plant. Uh, in terms of in Durban, for Durban Central, our water usually comes from the Midma Dam. Uh, from Pietermaritzburg. So at the dam there, they have a huge water treatment or purification plant. So it's treated there, and some of the water is treated there, and then some is treated there in Durban. From Pietermaritzburg, it then has to be brought to Durban. So after treatment, the potable water, you see the change in term there now, so potable water, because that's now drinking water. It then has to be conveyed via pipelines or aqueducts. Aqueducts could be huge pipelines, it could be things like canals or tunnels, and it has to be conveyed to the consumers of that water. The consumers of water may be residents in residential areas or towns, and also industries. Industries also consume large quantities of water, depending on the type of industry. The tanning industry is notorious for using large quantities of water. Food preparation industries also would use large quantities of water. Uh, the, so the conveyance of water from the treatment plant to consumers, so such as domestic dwellings, factories, industries, schools, hospitals, etc., is achieved through well-planned distribution networks. So we have these distribution networks. Now, uh, so sorry, I apologize for that. You can read through the notes. I'm not going to read through all of this. It's all written down for you there to read. So you can read through all of that. Right? Uh, so in the next paragraph, they may also be pumped networks or pump systems in your distribution network, and usually it's where yeah, our dams in certain localities would generally be located at a lower elevation because your rivers and dams are normally at the lower point. Water flows downwards, and you may need to now uh, um, convey the water to the areas that are high up, in higher at a higher elevation. So then you would need a pump in the network to pump the water to those areas. Uh, it's, in the South African context, generally our dams are built upstream because the land slopes towards the coastline. So if our dams are upstream, then we can achieve gravitational flow in terms of our main distribution, and we can avoid pumps. Um, I'll talk about pump systems just now. Right? So you can, I'll leave that. You can read through the introduction there, and yeah, it's all written there for you to read. The method of distribution. Now, generally there's three ways of distributing water. Uh, Three methods of distributing the water. The one is a gravitational system. In a gravitational system, we rely on gravity we, the, for we rely on gravity flow. The system is dependent on gravity flow, so there's no pumps in the system. So we're not using any other form of energy to achieve the distribution. Right, so it's purely gravitational flow, and that's the most common and that's the most economical form of distribution. In the South African context, also, that's what we would try and achieve. Even in Durban, that's what we would generally. That's the kind of the method that we generally have here. Right. So, by implication, it means you would have a reservoir at a high point. So usually that's why your reservoirs are at the top of a hill somewhere. You think of Durban Heights in Durban. So you have your reservoirs at the high points, and then from the high point, it then gravitates to the areas that need water. Right? So in your distributed system, you have gravitational flow. There may be a few areas that may be higher than your reservoir or your storage point, and then you would need to pump water to those areas. You generally would have an elevated water tower. You would pump the water to the elevated water tower, and then from the elevated water tower, you then get gravity flow uh, to your distribution areas that are higher than the reservoir, at a higher elevation than the reservoir. The next type method, that's the direct pumping system, where from your treatment plant or your water storage facility, you then pump the water directly to the users. Right, so you're not relying on gravitational flow there. So you're pumping water directly to your users. It's an expensive system because you now need to have pumps to pump the water, and then there's other complications that come with that with a direct pump system because, as you can imagine, uh, water usage is not constant at any particular time or on any particular day. The demand for water will vary as the day goes by. So during the day, from time to time, the demand varies. You get variations in morning, evening. Industries switch on, switch off, things like that. Industries will come into operation, go offline, things like that. So the demand varies. So those pumps would have to be variable speed pumps. So they would need to be able to pump as the demand increases, then they would need to pump more water, and as the demand decreases, they would need to pump less water. It is also very expensive. The pumps would use electricity. They would need energy, electrical energy. So an expensive system. The pumps themselves require maintenance from time to time. They need downtime. They need to be serviced, and the pumps themselves are very expensive. So as far as possible, we generally would avoid a direct pumping system or try and avoid the use of pumps in total if we can. Then you get the combined gravity and pumping system. And I've already spoken a little bit about it when I mentioned about the gravitational system, where you can have sometime in a gravity system to distribute water to certain areas that are at a higher elevation. You might install a pump uh, to and pump water to an elevated tower. But what this is referring to when you talk of combined gravity and pumping system, it means that at any point in your distribution system can receive water from a pumped system and from a gravity. You've got two sources of water that you're supplying water to one point, and one is from one side is you're getting gravity flow, and from the other side you're getting pumped flow like that. Right? So that's the combined gravity and pump system, and you'll see it a little further down in the notes. There's a diagram there, and you'll get more clarity on that. In fact, the combined gravity and pump system, the example in the introductory on the hydraulics one, I think it was example 4, example 5, I think, that we went through. As I explained to you there, that was a combined gravity and pumping system where you had a reservoir on one side and you had a pump on the other side supplying water to one point. Right? So you do have an example of that in your notes. Okay, now the gravitational system, so there's a little bit, again, you can read through these notes and the explanation is there. It's the cheapest system, as you can imagine. Right? You're getting the energy is for free, put it to you that way, right? If the reservoir is appropriately located, you will get gravity flow, and that's the only cost is in the maintenance of the pipes. There's no cost in terms of pumps or things like that. Right? It says if the topography is favorable, so that's topography, that's the ground level. That's what you're talking about, the hills and valleys and things like that. So that's what that would refer to. So water from the high elevation is distributed to lower elevations by gravity alone and without pumping. Right? So read through the rest of it. It'll be of interest to you. So you can read through that. The direct pumping system, again, I've spoken to you about that, and you'll see mention here about what I mentioned about the variation in demand. You'll see there at the bottom, continuous monitoring of pumps are required to run at various speeds, right? That's because you'll get variation of demand. There's repair and maintenance costs, there's downtime. So with the pumps, you actually need duplicate pumps, right? Because you need a backup pump if a pump breaks down or something, and they do need repairs from time to time. They do need maintenance from time to time. So that increases the cost of it also. So you will need a pump, and then you'll need a backup pump system also in that, and they all come at a cost, at a huge cost. So it will increase the cost of the water supply to that distribution area. And then the combined systems, again, you can read through that, go through those notes and relate to that. Right? The systems of supply. Now, when it comes to the systems of supply, there's two, what we call the continuous supply and intermittent supply. Right? Continuous supply means 24 hours of the day, and that's what most of us are used to. If you're living in the urban areas in South Africa, living in Durban, that's the kind of supply system where whenever you open the tap, you get water. Well, actually, more recently, with load shedding in certain areas, when there was load shedding, then they did not have continuous supply. The water was shut off. So those of you that were affected, I'm one of those, you would know what it means like to have an intermittent supply. Right? But continuous supply means, in theory, that you have water 24 hours of the day, unless there's a breakdown or some exceptional circumstances. So even with the load shedding, that's an exceptional circumstance, so it would still be continuous supply. Right? Then you have intermittent supply, and intermittent supply means that you only receive water for certain hours of the day. Now, in some countries in the world, usually third world situations or developing countries where there may not be sufficient water supply. There they would distribute only, for example, you may only receive water for 2 hours a day or 3 hours a day, and then you'd have to fill water into buckets or whatever and store water for use for the rest of the day. So you'll be able to do your washing or something quickly in that 2 or 3 hours, and then the water would cut off again, and then if you open your taps, there's no water. Right? So that's an intermittent supply where for certain hours of the day or for a few hours in a day. It's interesting with regard to this intermittent supply. In essence, it's a failed water supply system. And I'll talk a little bit about that. There's another book that I want to show you, and it's a South African book, so it's written in the South African context by the Water Research Commission. Let me just show you this book now. That's the book over here. And they have an interesting discussion on intermittent water supply systems over here. Right? And I'll come back to this book as soon as I'm finished with these notes and talk about it. Uh, I will give you the link for that book also. It's a very, very good book for you, and I strongly suggest you read through it. And I'll put the link for it also onto Moodle for you to read through that book. So this intermittent, it does okay. Why is an intermittent supply not so good? The first thing uh, is water is not available it's not always available when it's needed. Right. So there are hygiene issues with that. So, for example, if you go to the toilet and you want to flush the toilet, there may not be sufficient water available to flush the toilet. So there are hygiene issues. There are also issues with the supply system because the pipes empty out, right? When the water supply stops, then the pipes would empty out, and it then means you can then get seepage where there are weak joints or cracks in the pipeline. You then get seepage of contaminated water into the system. So it means you also then have a contaminated water supply system, and you can get contaminants from nearby sewage systems or stormwater systems or industrial systems where there's chemical pollution and things like that. And you could then, the water supply would then become contaminated. So there are lots of issues with intermittent supply systems. It is not an intentional design system, right? It usually means that there's some issue with the water supply, so that's why you have an intermittent water supply system. Read through that section there in the notes, and also there is a discussion on that in the book that I will show you just now. Layouts of distribution system. These are just broad layout systems. It doesn't mean that every town has this or has it exactly. Sometimes there's a combination of certain them, but it gives you an idea of the thinking of what goes around, how you would plan the overall layout system for a city or for a network, for example, multiple towns or city for a distribution network. Right? So, for example, in eThekwini itself, how would they, from Durban Heights, for example, the kind of distribution layout they would want, or for example, I'm gaining water who purify the water and they're the bulk water suppliers, for example, what kind of distribution layout they want. So it's on a bigger scale. It's not the small reticulation network within your suburb or things like that. It's the larger network that we're actually looking at over here. Right. What does the distribution system or distribution network consist of? The mains, now here we're talking of the pipelines, right? The water distribution pipelines. So you'll see that you'll usually have a main pipe. That's the main supply pipe. And then you have sub mains. So now it means the water is going to split out from the mains. You're going to take it out into sub mains, and then branches and laterals, and then the service connections is the actual connection to your house or to an industry or to a factory or to a school or hospital or something like that. That's the actual connection to that. Right. So you get the flow of water from the reservoir. Or your supply, usually a reservoir, it comes in the mains, and then from there, it's then going to split, or you're going to tee off into sub-mains and branches and laterals and things like that. The types of pipes that we would use, steel pipes, common in the South African context, but there are corrosion issues with that, so you need corrosion protection, cast iron. HDPE pipes now in today's time tends to be the most commonly used. The HDPE or PVC, these are types of plastic pipes. And then you get concrete and fiber cement pipes. Fiber cement pipes were common in the Durban area about 40, 50, 60 years ago. They were commonly used in the Durban area. They've now reached the end of their life, and they are brittle pipes, and many of them are giving problems in that they burst or the joints become loose or whatever. And so lots of problems with the fiber cement pipes currently, and they're usually being replaced with PVC or HDPE pipes. Steel pipes and cast iron, these are steel, they would rust because water does contain, the potable water does contain quantities of oxygen in it, dissolved oxygen. So if there's oxygen in the system, it will then cause corrosion of the pipeline. and these pipelines would then require some protective coating on them. Again, a discussion of the pipes, and especially in the South African context of that, the type of pipes, the advantages, disadvantages of these pipes. There's a very good discussion again in that book, this book here, Operation and Maintenance of Water Distribution Systems. I'll refer to it as the Water Research Commission book. It's published by them. The Water Research Commission is a organization that's set up by an act of parliament, and it's a South African organization, and they, as the name applies, they generally do research into water-related issues. So they have published that book, very useful book, and there's an entire chapter dedicated to this section on pipes, and I will refer you to that, to read to that one. It is the discussion of pipes and corrosion protection is one of the topics in this module. So when we come to that, I will refer you to that chapter. You can read that, and you can even read it now. I will give you the link for that book on Moodle. Right. So we spoke about the actual pipes. In large areas, right? So they talk of cities over here. So the larger distribution network, the area would be divided into zones, and then you would now need to distribute water to those zones. And how do you go about it? Generally, we see four different types of systems that are used. The dead end or tree system, the grid system, or they call it a reticular system. Then you get the ring or circular main, and then you get what we call a radial system. And from the names themselves, you'll see how, from the diagrams, you'll see why those particular names are derived. The first one, the dead end system, that's what you see on the screen now. Let's enlarge it a bit. Now, at the beginning of this section, let's go back and show it to you. We spoke about mains, submains, branches, laterals, like that. You recall that. So you'll find that symbols are used in these diagrams, and on the top right-hand side now of the screen of this diagram, you see those symbols: the main pipe, submain, branch, or cutoff valve, or things like that. Right? So you can see these are the symbols used for this network. So if you look at this system, you have a mains water supply pipe that's passing through an area. Right? You see the thick line in the middle of the drawing, where my cursor is at the moment. Let me just take out my drawing pen, make it red, make it a bit thick, just to assist with that. Right. So for the dead end system, you have your mains pipe.
Sorry, sir.
Yes. The question.
Apologies, sir. I don't know if it's just me, sir, but the page is stuck on that intro to operations and maintenance of water distribution. There we go.
Do you see are we back on the notes now? Okay.
Yes, sir.
Okay, thank you for that. So for the dead end system, you have your mains water pipe, so that's basically passing through your area like that. So, and you now want to reticulate an area from that. So obviously you're going to have to tee off from that. You then tee off, and the tee off pipe. So we're now looking at one particular area from it. So we're going to tee off like that. So that's your tee. What's referred to as the sub-main pipe. So you tee off from there. And if it's a sub-main pipe, so it's still some sort of a main, so it's going to supply water to other pipes. And then you have your branches from that. So now it's the branches that are actually going through your streets and roads and whatever, and that are supplying the houses from there. Right. So you're going to have the branches from there. And then from that, you then have your connections, your house connections, whatever, and you then connect up from there like that, wherever the properties are, or wherever the industries or schools or hospitals are like that, you would have like that. Now, if you look at the system, okay, so you have the mains that's passing through. Then we've got the sub-main, whatever that comes, and then we have a branch pipe that we go, and we come to a dead end. Notice that it's not returning to either the sub-main like that. It's not returning like that, right? So it's not doing that. It's not returning back to the main pipe like that, whatever. So we don't have this loop, right? So it means that there's only a one-way flow of water. from the mains pipe, it flows down the sub-mains, down the branch. The water can only flow in one direction. Any particular connection, house connection, or shop connection, hospital connection, whatever, any connection to that line the water can only flow in one direction to that point. Right? So there's like only one source of water, and that is that main pipe, the sub main that's branching off from the main. That's the only source of water to that one particular point. You see the dead end at the end there where I'm drawing a circle now. So that's the dead end of that branch like that. Uh, there are advantages to this kind of system and there are disadvantages to this kind of system. You would need, obviously, your mains is passing through. In the design of a network, you then got to allow for maintenance of the system, for pipe breakages, leakages in the pipe system. So maintenance and repair work would need to be done from time to time. So you would then need to install valves in your reticulation network system. So generally in this kind of system, you might install a valve somewhere, maybe at that point, so you can isolate that hole. If you need to do some repairs in that system, in that network there. And again, the positioning of those valves requires engineering judgment and experience. And as you get more involved in industry in the design of these networks, you will become more experienced in the the positioning of the valves. You generally have a certain maximum distance, so you wouldn't want to isolate an entire region one time just for one small leak that you would then cut off the water supply to an entire region. So you wouldn't want to do that. So you wouldn't have just one valve like what I've shown here, just off the sub-main branch. You then have to install further valves. So you might want to isolate, for example, the branch pipe. Usually that's where you would install a valve. Just my pen is quite thick at the moment, so maybe it's not showing it. I just want to show you. You'll come across in engineering drawings and in textbooks. You may not be aware of it. The symbol for a valve is generally, if you've got your pipe running like that, then the symbol for a valve, you'll see something that looks like this over here. That is, you can see it's like the water being pinched, like a pipe that's pinched in the middle. Right? And that's represents a valve. So that's the symbol that we use for a valve in water reticulation design. But that's just out of interest of it. So within the dead end system, you see you have a dead end in the system. Now, the advantage behind it is that usually it's cheaper because you would have less pipes. The number of pipes is reduced. You don't have this returning branch to your mains or sub mains or whatever like that. So you have some cost savings from that point of view, that you would have fewer pipes in your system. But it does have some serious flaws in it and disadvantages in it also. Because you only have one-way flow, the pipe sizes may be larger than you require. If you had a looped system, then you could get water coming to any particular area from multiple sub-mains, and then you could then get reduced pipe sizes. So, for example, if we were to close the loop here like that, if we brought it back to the mains, and then if you chose, for example, one particular point over here, it could then get water from this side. It could receive some water from this side, and it could also receive water from that side. Right. So you could then maybe reduce the pipe sizes because the demand, for example, on the sub-main branch here might be less because there's another sub-main branch that's also supplying that same point of water. Right. So in terms of the pipe sizes, you would generally in the dead-end system you would end up with larger pipe sizes than you have. So that's a disadvantage of it. You also have to a more serious concern with dead-end systems is what we call stagnation of water. So if, for example, certain industries or certain homes are closed off, whatever, somebody goes for a holiday and they're not at home, for example, in that area for 2-3 months, whatever like that, or the industry closes down, or they move out and some new industry will move in after some time. So maybe 4 or 5 months there's no water usage in that system. The water in that pipe that actually stagnates. It doesn't return back to the main system. Right? It's held there, and in that this stagnates over there. And then you could get water contamination. The water may have been chlorinated, but the chlorination effect would have been gone by then. So you can then get bacterial growth in those pipes and in the water at that time. So stagnation of water is a issue when it comes to dead-end systems like that. Right. So that's just a quick summary. There's much. You read through the notes, and there's further clarifications and explanations in the notes with regard to the dead-end system, the advantages and the disadvantages. Uh, this module does have theory questions in it in your exams and tests. So basically, all of this notes is theory that you would need to know. Right. So dead-end system. Again, yeah, please read through that. The next one. Okay, I'm waiting for the diagram to open here. Now, where is my diagram? Okay, let's just go back here. Okay, that is a blank section there. The next system is the grid system. And looking at the grid system from the diagram, immediately it'll become obvious. You see that shape, right? It's a reticular system, it's a grid system. And here, the dead end system, that was the first one, so you had dead ends over there. The next three systems you'll find are looped systems. Right? So you do have these loops, so water can flow to any particular area from multiple, can come to that from multiple directions like that. Right? So in the grid system, if you look at it, that we want to identify the mains pipe. So let's just go, let me just thicken the pipeline again, and then you'll see thicken my pen there. Right, so you have the mains pipe that's basically flowing through that area or through that suburb like that. So the main pipe like that. So that's the main distribution pipe that's distributing water, your main distributions pipe over there. And from this pipe, you then tee off and you have sub-mains pipes like that. So you'll have multiple sub-mains pipes. Okay, let me use a different color this time for that. So you then have multiple sub-mains like that tee off from this particular pipeline. They don't have to be directly opposite each other like what's shown in this diagram. So you have the sub-mains pipe. So for example, what I'm saying, that it can be like what I've shown now, like that over there. They don't have to be directly opposite each other like that. Right? This is just a schematic, so it's shown like that. So you have these sub-main pipes like that, the ones that you see in the blue. And so these are teeing off from your main. And then from these pipes, you would then have your branches that would now supply water to your connection points, so to your houses and industries and various hospitals or schools or whatever like that. So from the sub-mains, you then have the branch pipes like that. And okay, let's use a different color so it's easier to see. Right. So we then have these branched pipes like that. We then put these branches like that. I'm just drawing the first one like that, so it'll help to explain the context of it like that. Okay, so you have. Let's do the next one also, and you'll see why. So you have these branched pipes like that. And again, like I mentioned, they don't have to be directly opposite each other. Right? You could have, instead of the one there, it could be like that way I've shown over there like that. Right? So it doesn't have to be exactly as shown in the sketch like that. So, but the big difference this time is you'll see that if you choose any particular point, any reference point or any connection point on that, so let's choose one, and let me just get a appropriate pen color for that. So if let's say we want to supply water to that particular point, immediately you can see that water can flow to that point in that direction. It can come to that like that, or it can come from that direction like that. That's like that. So you've got this multiple supply of water like that to any particular point. Uh, you notice that you have a looped system. Notice that, so you can have water moving around like that. So you have a looped system like that. So you have these loops like that, and what we refer to that when you have water that can move around like that, we call that a ring main system. That we call it. It means we now have a ring main around our area like that. Right? So if you look at it, we've got these branches, and then we have the uh, the sub main. The sub mains pipe that's in blue, and then we have the branches. But you can go around the whole. You have this looped network like that. Right? So you have, and we refer to that as a ring main system. So you have a ring main around your whole supply area. So water may be cut off from one direction, from one side, but then you can get water coming from the other side also like that. Right? So that's what you have in these kind of systems like that. Just to show you something about the advantage of this kind of system. Firstly, because you now have water flowing from two directions, you can have smaller pipe sizes to supply water to a particular area. You also will have better, in terms of the residual pressure, you'll achieve better residual pressures at the point at which you want to supply water, because you can get water coming from two directions to that particular point where you're supplying water. Also, in terms of when there's a breakage in the system, or there's some maintenance being done in the system, then with the dead end system, sometimes an entire area is cut off and just to repair a small section of the work. Whereas in these kinds of systems, you can just isolate the relevant branch or lateral, and water can still be supplied to the rest of the area. So, for example, if I just want to choose a thinner pen, and just explain that to you. So, for example, let me just remove some of this clutter here. Like that. Yeah, okay. So, for example, say we have a breakage at this particular. Sorry, my pen again. My pen out. There seems to be a lag in my computer. Let's say there's a breakage in the pipeline at that point over there, right? There's a breakage in that point over there. Now, in this kind of system, one would generally install a valve like that at that point over there, and one would install a valve like that in these laterals or uh, branches that we have over here. So you could just shut off those two valves, and then you could carry out repairs to the pipeline at that particular point. And water, the area down here, they would still have water supply. They would not be affected further down there, further down the side. So they still have water supply. Right? So all of these areas would have water supply. It's only that green pipe that would be shut off like that. In a dead end system, then that wouldn't be the case. So depending on where you're, let me just try and show you what I mean by that. Let's say we had a dead end system like that, and so for example, we did not have the water did not return on the branch on the left hand side, like, you did not join it over there at that particular point, and you did not, for example, even at this stage, there was no branch between those 2 points. So you just had the sub main coming out of that and distributing water to those points over there. And if you had, for example, a breakage at that point over there, then usually in this kind of pipeline means you would have to shut off the water supply at that point over there. And it means that the rest of the area, all of that, whatever development would be even down the side. So you have fewer areas that whose water supply is shut off when you have these kinds of systems, the grid system, or what we refer to as a ring main system. The other systems that we look at now, you'll see it's just variations of how this main pipe comes through the system and the sub mains. There's variations in the sizing of it, where the sub mains is and where the mains are, and also where the actual supply, sometimes reservoirs are. In the next two systems, we look at that. And so this is the grid system. It's all explained to you in the notes. Read through all of those notes there, and you get a better understanding of it. Then now you see the word here being used, ring system. You see that the ring system. This one, generally, it's called a circular system, and this time you'll notice what's the position of the main pipe in this one, and you'll find that the main pipe is on the outer, the perimeter area of that area like that. Right? So look at it over here. That's your. This is the ring system, or what we generally talk of a ring main system, a typical ring main system. So similar to the previous one that we had, but this time, let me get a different pen color. And let's choose a red. Let's make it slightly thicker. So similar to that, we have our main pipe here, but you see the main pipe is not like going through the system like that. The main pipe then splits uh, into two, and it goes out. Think of it like the perimeter of the area like that. So that's our main pipe over there that's supplying the entire area. And this uh, loop here that in the middle that we have, this, okay, let me just change the colors, and then it'll be easier to follow. to understand the terminology. So we have this is the main, the one in blue. That's your main supply coming from the reservoir or your water treatment plant, whatever. That's the blue one that comes there, right? And then we split that main supply now splits up into two, and we have the red main supply like that you're seeing in this diagram, and that's what we refer to as the ring main pipe. Right? It's like a ring around your system, so that's the ring main pipe, and then from that pipe we then have the your sub mains pipe. You see the SM there, that's your sub mains pipe, and then from the sub mains pipe you then have you can then branch off, or you can connect up to your individual stands or industries like that over there. That's so the ring main pipe, that will be a large diameter pipe, the large, because that's supplying the area, the entire area from that, and then the sub mains pipe, those will be smaller diameter pipes that you have there. You then install valves in the system. You can see they're using these dots. They're not using the actual valve symbol. It's easier in the sketch to show it. So they just use the dots to indicate cutoff valves there. And you now have the ring main system over here. Now, what are the advantages and disadvantages is you have a much better, because you've got this large pipe on outer pipe here on the perimeter like that, so that's your ring main, you get a much better pressure distribution within the network itself. Right. So there's, because of the larger pipe, obviously the pressure losses would be less in the larger diameter pipe. So that's why you get this much better pressure distribution system over here. You also have any particular point can receive water from up to 4 to 8 different directions. It can come into any particular point. So, for example, if you take a point like that over there, water can flow in from that direction. Water can flow in from that direction, from the main. It can from the ring main. It can come in from that direction like that. Water can come in from that direction like that. You can also go in from this. It can also go in that way. It can come around like that, and things like that. So yeah, it has multiple supply points at any particular point. So that's why you get this much better pressure distribution. So you might have, for example, the longer one. You can see the longer route. That would obviously have more friction losses because you have a longer pipeline. So the pressure head may be lower. Coming teeing off from the direction that I'm showing you now, how my cursor is going, as compared to from the left-hand side when you come, it's a much shorter route for the water to come to that point. So you have lesser frictional losses, so you could have a higher residual head at that particular point like that. Right, so you get the main advantage in this is you have a much better pressure distribution and higher residual pressures. You can achieve higher residual pressures at any particular point in the network like that. The other advantages about in terms of multiple supply points, you can isolate just one point. So if you have a breakage at that point, again, if you have a valve there and you have a valve in the system like that, if you close those valves, the rest of the network is unaffected. And you can still supply water to the rest of the network, and you can just isolate the relevant area, easily isolate the relevant area. You don't have dead ends, so you don't have stagnation of water, things like that. So this is the kind of system that generally most designers would strive towards. Right? So this is the ideal world. Generally, this is the network, the preferred choice that most designers would try and achieve. Right? So the ring system, and commonly, if you're out there in the consulting firm, they'll ask you, "Do you have a ring main?" Right? When you're doing the design, first question your boss might ask you, "Do you have a ring main?" Right? So that's what they're referring to. The last system is the radial system, and in radial system, very different from the previous ones that we had. Right? So you have the main pipe. So, for example, so let me use colors here, and yeah, okay, we have slightly thicker pencils. So the first thing is, okay, you have a mains pipe that's passing through the area that you want to reticulate. So that's the main pipe that you have there, like that, passing through the middle of that. But then you take off sub-mains, and the sub-mains are not supplying any house connections or industries or anything with water. From this, you take off sub-mains, and you then supply water to distribution reservoirs. Right. So from this point, let me get a different color pen. We then have sub-mains, and the sub-mains then supply water to a reservoir at that point over there. And same thing, sub-mains over here. and supplies water to a reservoir. Again, this is just schematic. Those two don't have to be directly opposite each other. Right? Those two red lines don't have to be in a straight line. They can be staggered also. It's just the idea behind it. Right? So you take off a sub mains from the main, and you have the reservoir. You're supplying water to a reservoir. So same thing over here. You're supplying water to a reservoir, and same thing like that. I'm just purposely drawing it staggered just to show you they don't have to be in a straight line like that. Right? So you're going and you're supplying water to a reservoir. And from the reservoir, right, this we call a distribution reservoir. The sizing of these reservoirs, that's also part of the scope of this module. We will cover that also. You'll learn how to size a distribution reservoir. Okay, so you have this distribution reservoir, and you then reticulate from the distribution reservoir to the various areas, and you ensure that you have looped networks also. So now from the distribution reservoir, you see you've got all this, you're supplying water to multiple points, and you've got all these loop points. It doesn't have to follow this particular uh, this triangular grid system like what you see over here. The idea is just you have looped systems like that, right? So you don't, for example, even if like what you've seen in the red, like the red line, if you had the next one was like that, you don't have to have this line that I've shown over there. But so you have from your reservoir, you're still having these looped systems. So at any particular point, uh, let me just choose a different pen again. Let's try something like that. Okay. So at any particular point in the system, so for example, if you look at that point in the system, you can get from your the distribution water reservoir, the water can flow in that direction to that point, or you have in that direction. So you have multiple supply routes to any particular point in that network over there. Right. And that this is the basic idea of this radial system. Uh, it would now the fact that you got so many. If you look at this, you're going to a distribution reservoir and you're then supplying it. Obviously, this is not the network for your small suburb, for example, in Berea or Glenwood or Westville or something like that, right? It will not be that kind of system where you're going to have multiple reservoirs like that and you're taking. This is a much larger reticulation network. So this might be the town planners for Durban, the water and sanitation department in Durban. They would generally look at these kind of distribution networks. So it's a much larger supply system that you would be considering when you're looking at the radial system, right? Because you're building these multiple reservoirs, distribution reservoirs, and then from there you then the reticulating to smaller areas like that. Right, so these are the four. I spent some time just to explain it all to you. Read through it. In the text beneath it, there are all explanations. They give you the advantages, the disadvantages, and things like that. So you can read through all of that. There's some guidelines for design of a distribution system. We've spoken about these in the diagram that we generally break it down into three different kinds of pipes. We have the mains, the trunk mains, so that's the main supply pipe to the area. We then tee off from that, and then we have the feeder or the sub mains of that. And then we have our branches or laterals that go out and supply the consumers, your water consumers like that. So you can read through all of this, and again, it's something for you to read. I'm not going to go through it in this lecture here. But make sure you do read through all of that. The pressure in the distribution systems, the pressure would depend on the domestic use for fire demand, economic considerations, topography, future demand, and things like that. In this particular module, I'm not going to be looking at future demand, let's complicate matters for you. But in practice, when you're designing a system, you would look at what the future demand for a particular network is going to be. You may have fewer dwelling units there, but it may be a developing area, and in 10 years' time or 15 years' time, maybe there'll be many more dwelling units in that area, or maybe people might put granny cottages, and then now you'd have two units in a particular stand. So you need to, that's where, when you start looking at things like that, that's where you start looking at future demand. I'm not going to complicate matters for you, but in practice it is. It's not so difficult, but this adds a little bit extra complications for you at this point in time. You're still learning, it's just at the beginning stages, so I'll not burden you with that. But you do have to worry about the topography. That's what you got to live with. That's the terrain you are. For example, Durban is hilly. So your pipe's going to run over ridges, and it's also going to go into valleys. So that'll affect the pressure in your system. Economic considerations, fire. Again, that's a section on its own, the demand for fire. And the CSR guidelines give you the guidelines for that. When you're doing a development, you would also need to go to your fire station and get approval from them, and they would also offer you the guidelines that each individual metro has their own requirements in terms of fire or reticulation for fire demand. So you need to contact the relevant authorities in your area to decide on that. But there are guidelines in the red CSR guidelines also you'll find for fire demand. And then domestic use. So this table, you already have seen it when we did the dead end branch or the single branch design. So let's get my pen here. Give it another, use my highlighter, right. The maximum head in a reticulation network, we talk in terms of two conditions. We refer to the static head, and we would also refer to what we call the residual head in it, flowing in the water, so it's static in the pipes. Want to exceed 90 meters of head in our system. So that's the limitation that we put. There are many reasons for the limitations. From an economic point of view, the higher the pressure, the thicker the walls of the pipe would have to be. So you'd need a stronger pipe. Excuse me for a minute. My apologies for that. Yes, I spoke about the static pressure, generally 90 meters of head. That's the maximum that we would have. And there are many reasons behind it. Again, in the Water Research Commission book, you'll find some discussion on that. But usually, two main reasons. The one reason is to reduce water loss, to reduce water consumption, and to reduce water losses. But the higher the pressure, when you do have a breakage or burst in the pipeline, then obviously because of the higher pressure, more water will flow, so you'll have a larger wastage of water. So you'll have larger water losses. Also, during consumption itself, when somebody opens a tap, if the pressure is higher, then they would use more water. Right? So that is the main reasoning behind it. So, for example, if you're having a shower at home, and if the pressure is low, then less water would come out and you would use less water. You would generally still spend more or less the same amount of time in the shower, but you would use less water. If the pressure was higher, you would use much more water because you still spend more or less the same time. If you, for example, washing your hands, most people would tend to just leave the tap open while they're soaping their hands. So that water that's flowing out is just water that's wasted while you're soaping your hands. And if it's at a higher pressure, then you'd have more wastage. If it's at a lower pressure, you'd have less wastage. So that's the reasoning behind it. Also, from an economic point of view, a larger static pressure would mean you'd require stronger pipes to withstand that pressure, so those pipes would be more expensive. When it comes to the minimum head, residual head, you see that for the first line, that's the one that we generally would be designing for, because we have continuous supply in our houses. We're not looking at yard taps or yard tanks. In this particular module, we're looking at continuous supply, so it's only the first line in this table that would apply to us. The 24 meters of head, so that's the minimum pressure that you want under instantaneous peak demand. So this is after all your losses in the pipeline and things like that, your friction losses and things. So you get the residual head, and I have spoken about that in an earlier lecture. What is the residual pressure or the instantaneous peak pressure? This is the pressure. If you have to, while you're using the water, you put a piezometer in your pipe, if you have to drill a hole, put a piezometer tube there, then what pressure reading you would get. And the minimum value you want in your system is about 24 meters of head. That's the South African guidelines. That's also the guidelines for eThekwini. I think eThekwini might be down to 21 meters, if I'm not too sure, or maybe 24, but somewhere around there. Now, again, why do we have these maximum and minimum? So why the minimum? For the minimum, there's quite a few reasons for having a minimum. Certain appliances or equipment that use water may not operate well or fully if they're designed to work with a certain minimum water pressure. So you might have issues like that. But more importantly, you do not want to come closer towards 0 meters of head or lower pressures in the system, because you might get air as the pressure lowers in your pipeline. You'll get air bubbles or dissolved air from the water being released. So you will then have air in your system, and as the water flows and the air increases at another point in the pipeline, so the pressure increases at another point in the pipeline, those air bubbles will then collapse, and that collapse is usually dramatic, and it can damage the walls of the system. It's sort of like an explosion that takes place as those air bubbles collapse and go back into solution. So issues like that arise. You also don't want to come anywhere close to 0 meter of head pressure, because if you get negative pressure in the system, you can then draw water or contaminants into your pipeline. Right? You may have cracks, or you may have weak joints somewhere, and if you have the pressure gets lower, then you might suction in contaminants from the ground. You might draw in contaminants or soil or other polluted water into your system, and you then get contamination of your water supply system. So there are many reasons for having these guidelines: the minimum residual pressure or instantaneous pressure, and maximum static pressure in your pipeline. Right, so that's as a designer, that when you're designing your system, you would always be looking at what's the pressure in your distribution system. Right? So these are the guidelines you want. You'll be operating between these two values. That's what you'll be checking all the time. The design procedure, you can read it. It's outlined to you how you would go about designing the system. So generally, you would need in terms of the topography, you would need a contour map of the area where you're going to where you'll be reticulating or providing water reticulation. So you need a contour map or topographic map of that area. You would then need information about the existing water distribution supplies there, reservoirs, pump stations, where the roads are, things like that, dwelling units. You then have to evaluate what's the peak daily flow. So you'd have to calculate that or determine that, the peak daily flow. When we did that single branch supply, we did that, you'll recall. We evaluated what was the peak daily flow from a particular area. Remember, we even worked out the peak factor and things like that. Right? So we have to do that. Then you would assume a pipe size. Right, and then you would check the velocity of flow. You generally want it to be between 0.6 meter to 1.2 meter per second. That's the ideal condition. That's what the flow velocity is you want. But you can go up to about 3 meters per second. It's still acceptable like that to have those kind of speeds there. Right. Then once you've now looked at the velocities, you've assumed the pipe size, you would now take into account the friction losses in your pipe, and then look at again what's the you then allow for friction losses due to fittings in your pipe. You may have valves and the pins and things like that in your pipeline. You not may have, you will have. Any system does have those things. You'll have T's and branches and valves and various other fittings in your system. So you'd have to allow for friction losses through those fittings. And then you eventually work out, after all of that, the flow, what's the residual pressure, and then compare it to that table that you have at least 24 meters of head at that point, after that point. And then you would see, okay, sometimes the friction losses are higher, so your residual pressure goes lower. Then you then need to increase your pipe size. Right? Or you might even go into negative pressure, which means that the pipe size is totally inadequate for your system. If you get hardly any friction loss, and you might then, from a point of view of economy, you might decide, okay, you then try maybe a smaller pipe size. Yes, you'll get a little bit friction, you get some larger friction losses, but maybe you're still within the 24 to 90 meters ahead, and you might find that acceptable level. Right? So that's the general design procedure. You can read to that. It's a procedure you already, most of it you have been through when we looked at that tutorial last week. Right? Again, the design of a distribution system, you can read through all of this. It more or less summarizes what we've spoken about here, about computing of pipe sizes, about minimum pressures and maximum pressures or terminal pressures over there, that is the residual pressures and things. So read through this section, talks about the equations. In this particular module, we'll be using the Darcy-Weisbach equation or Hazel-Williams formulas. There are better equations than that. There's the Kohlberg-White equations, but what they call it mathematically, you've got variables. They are not. They have implicit solutions, not explicit solutions. So it's a trial and error method if you use some of the other equations. But there are books with tables, and you can look them up in the tables. But for this particular module, we'll keep it simple. So we'll look at basically the Darcy-Weisbach, the Hazen-Williams equation. That's the one we would tend to concentrate on. Again, read through this about the total loss. I've spoken about that, so you can read through that. And so this basically covers the section on design networks for you. And this set of notes is on Moodle for you, so you can go through that in Moodle. I did mention the CSIR guideline, that's also on Moodle for you. You see it does state the design criteria for water distribution and storage systems. We'll come to storage systems a little later, but for now, for the water distribution system, go through the section of the notes. It does give you the actual guidelines that you need to do. Most of what is in here, we've already discussed in those notes, but there are other aspects that you would need to know. Right, so you can go through this. I'll leave you to go through those guidelines. Then the third document that I spoke about was this operation and maintenance of the water distribution systems on the Water Research Commission. And I'll just show you the contents of it. All of it is not relevant to this particular module, but there are particular chapters. Most of them are, you'll find them of interest, and you can go to them. And I'll upload it onto Moodle for you. Not upload it, I'll put the link for you. It's available for free download from the Water Research Commission. So if you go to the website, you can download it yourself from there, but I'll also give you the link for that. But in this book, you'll find about the physical integrity. So they talk about the corrosion that can take place in pipelines, and that we will come to that. That's a section or the topic we will cover. That's the last section in water reticulation. So we'll talk about that, and they do provide a very comprehensive explanation or discussion on this section in terms of corrosion in pipelines and the integrity of the pipeline, and also you'll see the different types of pipes that are used in the South African context. They do have a very good discussion on that. About the different types of pipes, the advantages, disadvantages, and things like that. And then the hydraulic integrity, that's what we spoke. Now you have the actual reticulation network, about negative pressures we spoke about. We have pump systems, the residual pressures, and things like that. We will talk about air valves and things when we come to that. So air in the system, what its effects are, how harmful they are. We will talk about all that. So you have some additional notes. And when we do cover those topics, I will actually then refer to this section, these notes over here, refer you to them. Right. The water quality part, that's a different module that you do about water, another water module that you do. So you'd cover that. That would not be within the scope of this module here, the chapter 4 of this book here. The systems for managing operation and maintenance, chapter 5. Again, that's not, you can read it, it'll be of interest to you, but I'm not going to cover that in this module. The one on chapter 6, that's very relevant to this particular module. And it's something that, again, we will cover that. We will talk about that in one of the future lectures, not very far from today. that we will come to this and talk about joints in pipelines and about the pipes themselves and things like maintenance of the pipes and things that you need to do. And then this section on valves, I will cover it from this on valves and fittings. We will cover this from this particular module. So this will be a chapter that you would need to study, and we'll cover it from this particular module over here. Right, and the section on reservoirs and towers, again, you can read through that, but we will cover it. We have separate notes on that. We'll do that in the notes. And the section on pumps also, interesting, very relevant, but not within the scope of this particular module. And today we did water distribution systems. You can go to this very, interesting information you will find related to that. So let's look at that. That's on page 121. There were some things that I wanted to show you there. So, sorry, the page numbering is slightly different here. 1920. The water distribution system, about the hydraulics, we've spoken about it. They don't actually have the network diagrams the way we've spoken about it, but please read through this. It's additional information. It adds over and above what you've studied today, right? So you'll find, and it's all in the South African context also, about how you operate. You'll see, I had mentioned about a looped pipe network. So you find an explanation here about looped pipe network, about maximum allowable pressures in the system. There you're finding a discussion on that, about the maximum like that. So these are all very relevant. Minimum pressure in the system, why you would have the minimum pressure systems and things like that, why minimum pressure, about the velocities. And so you find further explanation on all those relevant things. So in the guidelines, they just tell you this is the minimum pressure, this is the maximum pressure, or this is the minimum velocity. So you find they give you possible reasons why those, or not possible, but they give you reasons why we have those particular guidelines. So read through this particular section. You'll find it informative, and you'll find it quite educational also. These topics where they talk about a water hammer, I will discuss that, explain that phenomenon in detail to you, so you'll have a better understanding of that water hammer. So yeah, please just go through this part of it. And then they talk of the maintenance of it, of these particular pipe distribution networks, and you can read through all of this also. I'll stop at this point. Any particular questions? Anyone has any queries or questions? Anybody? Okay, I think you might all be muted, so let me just, I don't know if you can actually ask a question. Just bear with me. Close transcript there. Participants, no. Okay, so you can actually. Your mics are not disabled. Yeah, okay, that's fine. Okay, if there's no further query, no one's asking anything, I can stop at this point. Let me stop the recording. You can still ask any. If you do have a question, you can ask it.